In this video, we'll start off with an example, and then we'll generalize the example in a corollary, and finally we'll state and prove a new theorem. So first the example. We draw a circle, which I've got for you, and then it says draw a chord AB. I've already drawn the chord AB. Here's point A, here's point B. And then draw a tangent to the circle AC. Remember what a tangent is. It's a line or line segment that touches the circle at exactly one point. And notice the point A here is the same as this one. So we need the tangent to the circle right here. So the only line that is tangent to that touches it at only that point would look something like this. I don't need to draw it all the way in both directions, but that's tangent. It touches the circle only at the point A. And since I mentioned I'll put C up here somewhere. So now we have a line. Again, I could have extended this line, but I don't need it down here. All right, so we have a circle. We've got a chord, and we've got a tangent to the circle, this blue line right here. If x is the measure of the arc AB, so here's the arc AB, and it has measure x. Then find the measure of angle BAC in terms of x. All right, so here's what we're looking for, the measure of that angle. Well, let's just first notice, I actually drew the center of the circle here, center being O, and I made a triangle with this chord. So we actually have a central angle here since the vertex is the origin. What do we know about this little triangle right here? Well, we know that that side and that side are congruent because they're both radii, each one of them is a radius of the circle. So we have an isosceles triangle here. And oh, by the way, since that's a central angle and it intercepts this arc, this central angle here is equal to x, the measure of this arc. Okay, so we're looking for this angle right here. Well, what I'm going to do is notice, what do you remember from an earlier video about a tangent to a circle, and then the radius of that same circle that touches the point where it's tangent? What do we know about this angle? So, basically, let me do a small version up here. You take a tangent to a circle, and then you take the radius of the circle that touches the tangent of the circle, that point where they're touching. They're orthogonal or perpendicular. So this, let me see if I can, making it look like a big right triangle. Okay, that's a 90-degree angle. And not only is that a 90-degree angle, CAO, but it's equal to CAB plus BAO. They're just two adjacent angles that together make up CAO. All right, so let's write some stuff down. Triangle AOB. We know it's isosceles. So what are its angles? What are the three angles? Well, clearly one of them's x. What are the other two? Well, those two angles, right there and right there, they are going to be equal because it's an isosceles triangle, and those are the base angles. So they're going to be 180 degrees minus x, and then we have to divide it by 2. Okay, so the sum of these two angles is going to be 180 minus x. Since they're two equal angles, we just divide that by 2. Okay, so those are the three angles. The 180 minus x over 2 is this angle, and this little angle right here. So now let's notice that, as we already said, maybe I'll write over, yeah, I'll keep going downward here. 90 is equal to the measure of angle CAO. Because it's a tangent and a radius that intersect at that point of tangency of the circle. Okay, but as we mentioned, what is the measure of angle CAO equal to? Another way, let's break it up into the sum of two angles, CAB plus the measure of angle BAO. Okay, so I wrote it CAB instead of BAC. That's the one we're looking for, BAC, this angle right here. And we know that this angle, BAO, has this value. Okay, so what do we have now? We have that, let's see, that's 90. So what is, I'm going to write this as the measure of angle BAC instead of CAB, only because that's the way it was written up here, same angle, is equal to 90 minus this one. Minus, and what is this angle BAO? It's that value right there. 180 minus x all over 2. So that tells us that the measure of angle BAC is, well, 90 is, you could say 180 over 2. 180 over 2 minus 180 minus x over 2, 180 minus 180 is 0. That just gives us x over 2. You can work out the algebra on this, the arithmetic. So we found the angle. BAC, this one right here, has a measure 1/2 the measure of this arc, which is 1/2 the measure of the central angle that intercepts that arc. Okay, well, let's just generalize that. We'll call this the chord-tangent intersection corollary. Here's our circle. If AB is a chord, draw any chord you want to. I just put the points A here, point A here and B here. Doesn't matter where you put it. Make the central angle if you like. You don't even have to. The chord, here it is, has some measure. And then what do we need? We need AC. We need the tangent. So the tangent will look something like this. Okay, so the angle we're looking for is this angle right here. And that angle that we're looking for is going to be 1/2 the measure of this arc. So I'll put C there. So the measure of angle BAC is 1/2 the measure of arc AB. And another way of saying that is that it's also equal to 1/2 the measure of this angle AOB. Because it is a central angle. So whatever this is in degrees, if that's x, then this is also x degrees. Okay, last theorem of this video, and it'll be a short proof as well. Instead of a chord and a tangent, we're going to have two chords in this theorem. So here we have two distinct chords, AB, so that means I've drawn the two chords. That means this is the point B here. And the other chord is CD, so that'll be right here. And they meet at point M. So it's, in other words, M is the intersection of these two line segments, A, B, and CD. That point right there, I'll put the M right there. What this theorem is telling us is that if you look at these two chords, this length times this length is going to be equal to this length times this length. Okay, AM times MB is equal to CM times MD. And let's do the sketch of the proof. First of all, which angles are a vertical pair of angles? Well, I could do, there are really two pairs, but I'm going to go ahead and call that one and that one the vertical pair. So we know that those two angles are congruent to each other. So I'll say the measure of angle AMC is equal to the measure of angle AMC DMB. AMC DMB. Okay, next we're going to look at the inscribed angle theorem. Okay, so that really means we've got to draw a couple more line segments. So I'm going to draw the line segment CA. So we're making a triangle here. And then BD, and we're making another triangle. Now we've got two triangles that we can see. And they have a common angle. At least the measure of this angle is the same as the measure of that angle. Okay, so now we have some inscribed angles. By the inscribed angle theorem, the measure of angle ACM is what? Well, first notice that the measure of angle ACM, it's exactly the same angle as the measure of as ACD. I'm going to put 2 bars here on this one. Okay, so ACD, what's the measure of that angle? Well, we got to look at this arc that it's an inscribed angle. It intercepts an arc, AD. So that's going to be 1/2 the measure of arc AD. Okay, well, notice also that this arc is intercepted by another inscribed angle, not just this one, but this one as well. Okay, so that's also equal to the measure of angle MB, let's see, ACM, I'll say DBM. We just used the inscribed angle theorem twice. Both of those angles, let me put the 2 notches on this one. Both of them intercept this arc AD. So that means they're equal to each other. So now what do we have? We have 2 triangles with 2 pairs of congruent angles. What does that give us? It doesn't give us congruent triangles, but it does give us similar triangles. So I could say that triangle ACM, similar, we usually use a squiggle bar like that to be similar to triangle DBM. I'll go ahead and say the reason by angle-angle similarity of triangles. Because that also means the third angle, the third angle pair would also be a congruent pair of angles. Okay, well, when you have 2 similar angles, 2 similar triangles, we know corresponding parts are not congruent, but they are proportional. And we know, for example, that AM over DM, they're corresponding sides of similar figures. AM over DM is equal to MC over MB. So they keep the same ratio because they are similar. I'll go ahead and just say by definition of similar triangles. Well, just by algebra then, if we just, remember when you have a fraction equal a fraction, it means the cross products are equal to each other. So that just tells us that AM times MB is equal to DM. Let's see. I'll make it look just like this. Remember up here, CM is the same as MC. So I'll write CM times MD. Again, all I did was, when you have a fraction equal to a fraction, their cross products are equal. And this is exactly what we were trying to prove.